Headers extension is probably correct, yeah.
Yeah, so the words are turned around. That's like a Latin kind of thing. Well, the good thing is, I guess, that IPv6 is still there, so it doesn't matter. This would still get accepted anyway. For the non-Irish people, this is the title in a slightly more normal language. I guess the most important thing here, this is a collaboration with Chestnut, specifically with Petavelo. So, let's go. This session is called Security and New Protocols. So the perfect opportunity to also make a joke about what's new, because nothing is new, because IPv6 is 20 years old. But, well, unfortunately for a lot of people, using IPv6 is still rather a new thing. I guess this is something familiar for most of you. I hope this is something familiar for most of you. This is what v6 looks like on the wire. This is new, this is different than v4, right? And something that is really new and different from v4 is this so-called extension header thingy, right? So when you quickly change, you can spot the differences, and you see that the next header field here now points to something which is called an extension header, and that the let's say the normal upper layer, so for example UDP or TCP, is not there, but instead there is a extension header payload which carries some kind of extra information, which is an extension to a normal packet, right? Below that is your original upper layer, so again TCP, UDP, or whatever, right? So this is what I'll talk about today. To give you some examples of, or well, all the examples actually of extension headers. This is the list, the first so many as defined in the RFC 2460, and as you can see in the last column, there are some extra things defined in this IANA protocol overview list, right? One of the most important things here is protocol number 44, fragmentation. This is an extension header in v6, right? So this is really different from v4, and we'll see a lot more about this kind of stuff. So what's the situation? Many operators are scared by extension headers because they can be misused for some things. And in most cases, if you drop stuff, things seem to work perfectly fine. So, you know, we'll just drop everything. And there are big companies, there are banks in the Netherlands that have this policy. They just drop everything that contains extension headers. Is that a good thing? We'll see. So what's happening in terms of research, there have been a lot of active measurements, or a few of active measurements, you know, trying to send packets with 1 or 2 or 3 or 8 extension headers across the internet and see, do I receive this packet on the other end? Turns out that indeed a lot of operators drop things that contain extension headers. So these are active measurements, and they don't tell us which extension headers are actually used in, let's say, normal traffic in the internet, right? So that's what we want to look into. So what do we want to know? We want to know what is actually behind or below, or right, these extension headers. I highlighted behind, we'll see that in the next slide. Why is that? We want to know, should you indeed drop this traffic? Is it all scary traffic that's behind these extension headers? And do we observe malicious things in there? So, to go into more detail, we are fond of flow-based measurements at university, right? We do a lot of flow-based stuff. But if you use a flow-based, aggregation-based measurement technology with extension headers, then you will actually lose information. In the first place, you hide information. We'll see that on the next slide. Why is that? And you aggregate things in a certain way that makes flows look bigger than they actually are, because you actually merge multiple flows into one. What we need to do is we need to fix this for our measurement appliances, right? I mean, this problem was there for forwarding devices, it was there for middle box security devices. we need to traverse this extension header combination to get to the actual higher layer payload. And I think it's quite critical that we do this for our measurement appliances, because otherwise we have no clue what's actually happening in our v6 internet. So to make this more clear, we got the classic 5 tuple, right, that's used in flow measurement. So we have a source and destination IP address, a source and destination port, and a protocol. So for example, yada 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 yada, TCP. Now, we have a extension header inserted into that packet. If you use your, let's say, normal naive, I don't know how to pronounce it, flow exporter, you will see the source and destination IP address, but you won't see anything that's in the actual upper layer, right? Because the extension header is on that spot now. So you don't have a source port, you don't have a destination port, and the only thing you see is what's in the next header field of the IPv6 packet, which points to the extension header, which is in this case protocol number 44, fragmented IPv6. So you lose the layer 4 source and destination port, you lose the layer 4 protocol, that's the information that's what I call hidden. And at the same time, everything between these two hosts that is fragmented will be aggregated into this one big flow record. So if we have fragmented traffic going on, you know, between our computers, if those are 100 flows, they will all be summed up and we'll have one big flow record. And this is troublesome if you use flows for things like intrusion detection or compromise detection, where your algorithm is based on the number of packets in a single flow. This is not a single flow. This is a measurement artifact. So, what we did. We have a very nice device. It's an IPv6 exporter. If you don't know IPv6, think NetFlow v10. And we created a plugin to extract extra features, to extract the things that we want to know. So that's, first of all, some metadata about these extension headers. So the number of extension headers in a flow, the size of the extension header, and the order of the extension header. Then we also extracted the actual upper layer stuff, right? So we did this traversal. We jumped from extension header to the actual upper layer. We extracted the source ports, the destination ports, and the protocol. And for TCP and ICMP6, we also extracted some extra stuff. The collector we're using is IPv6 call, the analysis is done using fbitdump. If you're familiar with flows, you probably know nfsen with nfdump. These are, let's say, the equivalents of that, but then for IPv6 stored in a fast bit format. This is all developed in the Czech Republic. Actually, Petter developed a lot of this stuff. So developing this plugin is to extract all the stuff is one thing, and that's painful enough by itself because it's C and I suck at C, and the stuff was not documented, right? But there's more to it, because if you only extract the stuff and you use your normal flow cache management thing, you will lose the information again, because already at the collector you should update the counters in the right way and incorporate the newly identifying features, such as the upper layer protocol, right? So you need to extract those things and you need to incorporate them in your flow cache key, right? Which is normally a hashing of all the features that you want and that is actually defining your flow. Good. So after a couple of months, that seemed to work. So we started measuring. We started measuring in our own campus network, which has both office building but also student residences, and we measured at Chestnut. It's roughly 1 month of unsampled flow data, and there was no filtering happening on any of those links. So the interesting parts, what did we see? This only concerns v6. We were not able to store a month of v4 and v6 stuff, and we were not interested in v4. So this is only v6. What you can see here is that The majority of flows do not contain an extension header, right? So that's 99.3 for chestnut and 99.9% for UTNet. Not really a big surprise. On the other hand, if you look at chestnut, we are closely reaching the 1% in terms of numbers of flows that do contain one or more extension headers. So what's in there? Probably in the back you cannot read this. This is all in the paper. The most interesting part is that, and this might be expected actually, is that fragmentation is the most common occurring fragmentation extension header. And UDP is actually the upper layer that we extracted from that using our plugin. There's some other things going on here. Of course, we see fragmented. We see fragmented TCP, which you might not expect. We see ICMP with 0. That's hop-by-hop options prevended. There's ESP, right? So IPsec, which is also an extension header. We see that in our university network. And there was someone who really liked fragmentation and fragmented his fragments. I'm sure there's a meme in there somewhere, but let's not go there. So, if we have so much fragmented traffic, we want to know what is in the fragmented traffic, because this information was hidden, right, with our off-the-shelf naive flow exporter. So now with our plugin, we can actually look into that. So we did a port analysis. And what I will show you is a distribution of source ports and destination ports that we saw in both of the networks. And these will be graphs with a lot of information in them. So just a trick. The solid lines are for source ports. You don't have to repeat me. And the dashed lines are for destination ports. Yeah. So let's see. This is our network, UTNet, the campus network, UDP. This is a line on 1024. So we have ports on the x-axis, and what I want to show you here is that there is a big difference on where the source ports are in this distribution and where the destination ports are in this distribution. Alright? The most interesting thing is where are the jumps, of course. This might be hard to see if you're behind this thingy, but this is port 53. Might be a surprise, might be not. So that's DNS most likely, and we see some stuff happening at 443. That is likely to be Google Quick. There are some other things. This 51 something is, I think, transmission, the BitTorrent client, and we see a pattern that roughly matches with most of the ephemeral ports. Those differ per operating system, but this is well, not really a surprising distribution. If you look at chestnut, we see similar things. A lot of DNS. Even more quick, some other ports, I don't recall what that application was, it's in the paper. But again, also jumps in the ephemeral ports. TCP, that's a lot of HTTP and HTTPS. And also here, we see that the solid lines, so the source ports are, most of it is before this line of 1024, and destination ports are more, in the higher ports. Chestnut, same thing. What I found 8333 that has something to do with BitTorrent, or that's what Google told me. I'm not sure if we have any BitTorrent miners here that know more about this, but it was quite a jump. And I guess the main takeaway here is this line of 1024. What does it really tell us? Again, this is fragmented traffic, right? If you have a service enabled, which is typically on a port lower than the 1024, it's very likely that you get small requests and you give out big answers, right? This matches with what we see in these CDFs. So if you decide to drop everything with extension headers, what does this mean from the perspective of let's say, your daemon, your server application? you will see a request come in. It's a small request, it's not fragmented, right? That's what we can see in the CDF. So it will reach your server. The response is very big, we will send it out fragmented, right? That's what your network stack does. So there's an extension header injected, protocol number 44. Now if you drop everything at the edge, the request came in, was handled perfectly fine, but it was dropped at the edge, and your server log is not logging anything, because everything went fine, according to plan, right? So this will be very hard to troubleshoot. So if you think you enable or enhance your security by dropping these kind of things, you might run into a lot of trouble later on. Another thing is that if you look at, let's say, the types of traffic that are served, HTTP, well, there can be malicious stuff in there, of course. HTTPS, DNS stuff. These are protocols that are likely to be very legitimate, but moreover, they are protocols that directly affect quality of experience for end users, right? So again, if you drop these kind of things, you're really impacting them. So do we see any misuse? I got some questions from operators like, do you see 4, 5, 6 chained extension headers? Because my router will run out of memory and you have a denial of service attack, yada yada yada. Well, actually, we found at most 2 extension headers in the flows in our measurements. For the UTNet, it was only fragmented ESP. That, well, seems to be legit, right? For chestnut, we saw a lot of different combinations, but yeah, what you see here seems to be maybe corrupt packets even, or I don't know, one-shot measurement trial thingies. Most of it is fragmentation. Oh, sorry. Fragmentation prepended by hop options, where the actual upper proto was ICMP. That is a strange combination. But it's not something that will break your forwarding device with only 2 extension headers. So I don't think this is reason for concern. Another thing that we observed and that operators are scared about is the size of the extension header, because you have limited memory, and if you're going to parse them, well, will things work? In all these flows, and if you remember from the overview, that's 2 something G flows, right? So that's a lot. There were, and this is in chestnut, roughly 180 flows that had a size that was standing out. Most of these extension headers are 8 bytes in size or 4 bytes in size. So 180 were bigger than 256 bytes, and there's a handful of them that was even larger than 1460 bytes. If you add 40 bytes for the V6 header, then you already exceed the MTU for a lot of things. So that's really dubious. Problem is, we cannot traverse the header chain there, because if you jump to a spot that actually behind the actual packet, it doesn't work. You cannot extract any upper layer info if there is any in there. Then this guy or girl that really loved fragmentation and did this inception fragmentation. We looked into this because, of course, we had the upper layer protocol, we had the upper layer ports, right? Turns out, those were three flows. They all originated from port 80, and it was all communication between 2 and the same hosts. There were 3 different destination ports, so that's why we saw 3 flows. So these could be a couple of things. There is this theoretical evasion attempt, right, where if you add enough headers that maybe a middle box is not able to parse it and it's just accepted. I don't think this was the case. What are you going to do with 3 packets? They were 76 bytes. I think it's highly unlikely. I think a network stack that just lost its way is far more likely. And I don't think this is a reason for concern, but it's definitely nice that we now can look into this kind of traffic. There's more in the paper that I didn't touch here. We did a short analysis on what are the ICMP types and codes that we observed in this traffic. We looked at the fragment sizes. Turns out that there is a really high jump in the CDF, so to say, on 1280. So that seems to be like a default value that Stash used for the first fragment. And most, if not all, of the fragmented traffic had at most two fragments in total. And there are many large tables with many numbers that were a headache to make in LaTeX. So, wrapping up, like I said, there is, I guess, if you count 1% as significant, a significant share of traffic in v6 that contains extension headers, which is directly affecting end-of-user quality of experience. So, I would say, please do not just drop your extension headers. If we look at hardware, and I'm not a hardware design guy, so it's hard for me to judge this if this is even possible, but if you could process one extension header in hardware and just, you know, use the slow path if you see more than the first extension header, it seems to be that that would be sufficient. Again, I'm not sure if this is really feasible in hardware design. I'm not into that stuff. But the whole denial of service thing doesn't really seem to be a problem. And last, but I guess this is maybe the most important thing, if we adapt our measurement approaches and technologies so we can actually parse the extension headers and see what traffic is there, then we know what is in our network, right? Because now we don't. And we are ready to detect these kinds of misuses. Because we didn't see something now. v6 is still not used that much, right? But it would be nice if you would be able to see all of these nasty things before we are flooded with them. So with that, that's the end of my stuff.
So, this might be in the paper. I haven't read the paper in advance. But where are you, or would you be able to do the related analysis on ICMP packet to big messages?
Packet to big messages?
Yes. Presumably the trigger for most of the fragmentation.
Yeah, so what is your question exactly? Do you want to...
What I kind of want to know is more about PMTUD collateralizing in the current internet, and whether you see packets to big messages that don't trigger the fragmented flow in response.
Right. That would be interesting. I think for the yeah, I think you would be able to do that. I'm trying to think if we do have, let's say, normal ICMP in this data, yes or no. But I guess that's definitely possible, yes. Yeah, and with the plugin, so it will give you all the stuff, so the fragmented ICMP, but also the hop by hop option, prepended ICMP, which is apparently a big thing in some networks. We would be able to get all the types and codes out of those. So.
Did you conduct active scans to see how many of the IPv6 packets with extension headers are dropped on the path?
No, I mean there have been some studies that, or do you mean our specific network paths? Because there have been some studies that you know, shoot out packets with one or more extension headers and measure at the other side, like, do we receive them? But we wanted to see what is, you know, what's actually used. So
yeah, I think it would be also interesting to see how much of the IPv6 extension headers they're trying to be sent you're actually see. How much of the packets that are trying to use extension headers are actually then arriving into the network.
that's a different study. What we wanted to do is really look at what is, how are they used in a normal, day in the internet, lived life of the internet. That's what we were after. There are some references in the related work that tries to do these more active kind of things if you're interested in that. I know you are interested in active measurements. So.
I sort of disagree with one of your conclusions where you say that there is not to be worried about the fact that extension headers are not a problem. I mean, I hope you do a backup of your stuff, right? And I hope your disk is working. So you do the backup because in case the disk is going to fail. Now here we are saying that we didn't see any attack, but this is not saying that it's not going to happen, right?
Yeah, that's true. That's what I mentioned as well.
So when you were concluding extension header are not a problem, I don't know why the ISP are dropping them. I would be more careful there, let's say.
Yeah, I see where you're hinting at.
The fact that you don't see anyone robbing PCs in this room doesn't mean that it's not going to happen.
I agree. No, I completely agree. But the consensus that there is right now is that it's a best current practice to drop everything with extension headers, and I guess we can show with this work.
Firewall in your network.
Come again?
It's a best practice to have a firewall in your network, to run a backup on your disk, to lock the door. So you want to avoid problems.
Yes, but you also want to avoid problems in another space, like your end users that you are now actually giving a hard time. So I guess there's a trade-off there.
Actually, I have a follow-up on that, if you don't mind. So you conclude that some of this traffic, if you were dropping traffic, you would impact on user experience.
Mm-hmm.
How does, is there any way well, you didn't kind of measure, is there any happy eyeballs kind of things going on here, right? So it could be that somebody is sending, it could be that the traffic that's being dropped is being replicated in V4 and not impacting.
Yeah, no, we didn't quantify the actual quality of experience, but if you look at what protocols are mainly in this in this case fragmented set of flows, then it's, like I mentioned, DNS, HTTP, HTTPS, which directly affects.
Unless the browser is racing the
IPv6
like that. And quick and H2 and which is kind of what they do. Right?
Yeah, will they? I don't know. I don't know.
Yeah.
I don't know.
I guess the only way you can tell from the V6 only traffic would be if it drops, so you can't really tell. Right? It's kind of, but I guess there would be an interesting measurement there to see, is there, of the stuff being dropped, is there an analog of the same kind of actual transaction?
Yeah, that would be a nice follow-up, yeah.
I might have two small comments. One is that you see a lot of DNS fragmented traffic here, and you might be able to, if you have, my guess is that this should be announced in some kind of eDNS extension about how big it thinks, how big packets it can transfer before doing fragmentation and things like that. So it might be possible to pull out some of that information and see if the fragmentation size is matching what the upper layer thinks is possible. And then the other comment was, I have seen a drunk Cisco router that was encapsulating stuff in protocol 41 multiple times before sending it to me, which looks quite like your multiple fragmented things here. So a drunk network stack sounds plausible.
Okay, that's nice. Nice. All right. Did you see a lot of that, or was it like we saw three flows?
It was somebody was sending me an IPv6 tunnel. And it suddenly stopped working, and when I TCP dumped it, I saw it was encapsulated multiple times, so I changed the network stack at my end, and it started working, and they didn't want to reboot their machine, but when they rebooted it, it went back to normal again. So it was
that sounds
a weird operational thing.
Yeah. Cool.
Other questions? So I have another one. Did you see any totally undocumented extension headers?
Well, there is this, where is... Okay, I'm already lost. So there's this experimental part, right, defined by IANA, and I think we saw like a handful of those. if that counts as undocumented, well, I leave that up to you. And I think yeah, so you see two here, but it wasn't significant or anything.
Okay, so there's nobody squatting on one of these code points that you saw.
That we saw, yeah.
Right.
Yeah.
Interesting. Anyone? Not? Then we'll thank you again. Thank you.